we're going to be finding the slope and equation of a tangent line, this time implicitly. So it's the same stuff. We find the derivative, we plug in our point, and it gives us the slope of the tangent, just like we did before. So we take the derivative first with respect to x, because that's our denominator, dx. So we get 2x minus, and then that's a product rule. So let's change that to a plus, and we'll make the 3x the first one, and then the y the second one, like that. And the way you can tell it, again, it's two letters being multiplied together. There's a little dot in there, like that. All right, so derivative of negative 3x would be minus 3, and then derivative of y would be 1. But again, you got to write dy dx. I made this line really large down here. All right. So now this would become negative 3y, so these two multiplied, minus these two multiplied, sorry, plus these two multiplied. So minus 3x, and then now we'll change that to a y prime, so like that. All right, let's bring down our 2x so we don't forget it, and now we can continue on. So plus, and then that would become 3y squared, y prime. So that is our y cubed that we just took the derivative of, the end there. And then now we can move on to the other side of the equation. It's a constant, so we end up with 0. So let's bring everything down. We should probably make this a dy dx just so that we know what we're taking the derivative with respect to. Perfect. Equals 0. Okay, and now we can plug the 0 in for x and the negative 2 in for y, and then just solve it for y prime if we want, but we're going to keep our pattern going because it's not a difficult solve. So we're going to leave the negative 3x and the 3y squared on this side, and we'll move the other non-y primes over. So this would become 3y minus 2x. Now make sure that we change signs here. So minus 2x plus 3y looks good. And so our y prime equals 3y minus 2x, numerator, negative 3x plus 3y squared. So that's just our first part here. We found our derivative, and again, this is the slope of our tangent. And we can plug in 0, 2. So now we're going to take 0 and negative 2, and we're going to plug it into our y prime. That gives us 3 times negative 2, 2 times 0, negative 3 times 0. So x's are zeros, y's are negative 2. And then we just simplify, which gives us negative 6 over 12, which is negative 1/2. So we just found the slope. So again, we have some curve. At 0, negative 2, we get negative 1/2. So the slope is negative 1/2. We can circle that as our first answer. That's the slope. And our point is 0, negative 2. So now if we plug it in, y minus negative 2 equals negative 1/2, x minus 0. And so we end up with y plus 2 equals negative 1/2 x. And so y equals negative 1/2 x minus 2. And then we plug it into Desmos, and you can see there's our equation. There's our other equation, and it hits perfectly. The nice thing with Desmos is if you click on any of the functions anywhere, you can see that it tells you where they intersect. So it's an intersection there and there, but that's it. So we know that this is our perfect tangent line going through our curve. And so there you have it. So once you take the derivative, it gives you the equation for the tangent line, the slope of it, and then we can use that to find the equation of a line. Now what I was saying before is if you take this equation and you plug in 0, negative 2 right off the bat, then you could just plug 0 in, minus 3 times negative 2, minus 3 times 0. So I'm just plugging in my x and my y, because it's already a formula. Let me plug that. I didn't plug that y in. That y is negative 2. You can see that the same values. All right, this would become 0 plus 6, and then that's 0 plus 12 y prime equals 0. And so now you can just say 12y prime equals negative 6 divided by 12 divided by 12. So you don't actually have to solve and find the equation, you could just plug the numbers in and go for it. Though the point of doing the solving is if you had multiple points to plug in and you'd want a nice little formula, you could just plug them in and it'll spit out slopes of tangents. Or if you wanted to be able to graph the derivative. All right, there you go.